What's up, interweb? We're going to go over the stuff we went over on Tuesday, the 1st. Today's Groundhog Day. 2222. 222. Yeah, whatever. Okay. Our roots are square roots. We have this. There's a 2 in there. We typically do not write that. And 5, where the square root symbol is called the radical. The 2 is called the index. And the 5 is called the radicand. Not super whiz-bang important, but we are going to use these words. Okay, so what if we have now the product rule? Of course, product means to multiply. So if we have the square root of 3 times the square root of 5 is the square root of 15. Or we could write it as the square root of 3 times 5, which of course is 15. We'll put it under the same radical. And if we have the square root of a times the square root of b, this is the square root of ab. And again, when there's no index in here, it's assumed to be a 2, or the square root of. Now, what if we have the square root of 2a times the square root of 5b? Okay? We can write this under the same radical. 2a times, excuse me, 5b, which is the square root of 10ab. Okay? Okay. Now, the quotient rule is basically the same thing. If you have the square root of c over the square root of d, you can put it under the same radical, a great big one, c over d. Right? Right. And what if we have the square root of 16 over the square root of 25? Now we can write them under the same radical, 16 over 25. Now the square root of 16 is 4. Square root of 25 is 5. Right? Right. And you could just leave it like that. Okay, simplifying roots. Now I'm going to go pretty fast on this because you can stop and start it. Of course, you know better than I do. Plus the fact this recorder will only give me a certain number of minutes to record, so I'm going to have to go kind of fast. So if we have the square root of 8, what we want to do is we want to factor the 8 into two numbers where one of them is a perfect square. And the perfect squares, I sent you a sheet on those. First divide by 2, then by 3, then by 4, then by 5, and like that, and see if you can get a perfect square. So if we divide 8 by 2, we get the square root of 2 times 4. And 4 is a perfect square. So this is going to equal, the square root of 2 is the square root of 2. We don't know, we don't care. And the square root of 4 is 2. Once you take the square root of it, it comes out of the radical. Because we have the square root of 4 times the square root of 2. You can break it down like that. And the square root of 4 is 2. And the square root of 2 is, we don't know, we don't care. Now, what about if we have the square root of 32. Divide by 2 and you get 16. Is 16 a perfect square? Yes. So we have the square root of 16 times the square root of 2. And of course, those can go into the same radical if you want. Square root of 16 is 4. And the square root of 2, again, is we don't know and we don't care. Okay, and again, remember, when you have the square root of 16, why is my recorder? Why is my recorder not going here? Okay, let me do this one again because I think my recorder may have paused itself. If we have the square root of 32, divide by 2, and this is going to be the square root of 2 times 16. And 16 is a perfect square. We could also write it the square root of 16 times the square root of 2. And again, it doesn't make any difference what order these are in. The square root of 16 is 4. Square root of 2 is, we don't know, we don't care. Leave it under the radical. Okay? Now, what if we have the square root of 50? Divide by 2 and you get 25. 25 is a perfect square. Square root of 2 times 25. Or we can write the square root of 25 times the square root of 2. Square root of 25 is 5 times the square root of 2. Okay? Okay. Now, what if we have this? The square root of x squared. Now remember, what does square root mean? What number times itself? What number times itself is x squared? This is x. Really, essentially what we're doing is we're taking the index, which is 2, dividing it into the 2, which is 1. What's that? We don't write it because we're lazy. Okay, now what if we have the square root of y to the 4th? Well, what number times itself is y to the 4th? Y squared. Because remember, we're taking the 4, dividing it by 2. Okay, now remember, y to the 4th is y times y times y times y 4 times. Okay, and now what if we have an odd number here that we can't divide by 2? What if we have the square root of a to the 5th? Now we can factor a to the 5th into the square root of a to the 4th times a. Okay, a to the 4th. So this is going to be, we can rewrite this, square root a to the 4th times the square root of a. We can break them up, excuse me, a to the 4th, the square root of a to the 4th is a squared. Square root of a is just the square root of a. Okay, so factor the 5, and then take the square root of it. Okay. Now what about square root of d to the 7th power? Again, we need to factor d to the 7th into the exponent needs to be an even number. So this is going to be the square root of d to the 6th times d. Now d to the 6th is the square root of d to the 6th And you don't need to break them up like this. It's really pretty simple. D to the square root of d to the 6 is d cubed, or 3 times the square root of d. Can't take the square root of that. Right? Right. Okay. Okay, now what if you have this? This is called the cube root. The cube root. There's a 3 as the index into k to the 6th. Same process here. We're going to divide the 6 by the index 3, and we get k to the, what is it, squared? Yes. Or if we have the square root of m to the 12th, I'm sorry, cube root of m to the 12th. That's going to be m to the 4th. We're going to divide the 12 by 3. And same stupid kind of problem. What if we have the cube root of n to the 7th? Now we're going to factor the n to the 6th. Now we want a number that's divisible by 3. So we're going to take the cube root of n to the 6th times n. So this is going to be 6 divided by 3 is 2. So we have n squared times the cube root of n. Okay, what we did here is we took the cube root of n to the 6th times the cube root of n. I'm sorry, I got this too small. Excuse me. Okay. Okay. All right. Now, Pythagorean theorem. Pythagorean theorem. When you have a right triangle, pretend this is a right triangle. Little box in the corner means it's 90 degrees. This side over here we typically call A, this one we call B, and this one C. A and B, it doesn't make any difference which one's which, but C, the hypotenuse is the longest side, opposite from the right angle. This one has to be C. Now, the Pythagorean theorem states a squared plus b squared equals c squared. So what if you have this? Again, pretend this is a right triangle. This is 3 feet, 4 feet. We don't know how many feet. Okay, so what is the length of A? Now, A is this one. This is A. This one's B. And this one is C. So A is 3. So 3 squared plus 4 squared equals C is x squared. Now it's just order of operation. Oh, sorry. 3 squared is 9 plus 16 equals x squared. 9 plus 16 is 25 equals x squared. Now we don't know, we do not want to know what x squared is. We want to know what x is. So we take the square root. Whatever you do to one side, you have to do to the other. So 5 equals x. Does it make sense? Is it reasonable? If you don't do anything else, just make sure that the hypotenuse is the longest side. Is it? Yes. 3, 4, and 5. Okay? Okay. Now for right now, if you see a right triangle, you're probably going to use the Pythagorean theorem. And when you get into geometry and trigonometry, not necessarily. What if this is 6 feet? This is 10 feet. Okay. Now remember, this one is our C. These are A and B. So A squared plus B squared equals C squared. This is about as difficult as these problems get, and it's really not very hard. So A squared is 6, so we have 6 squared plus our B is X, we don't know, and our C is 10. So we have 36 plus X squared equals 100. Now we have a real simple algebra problem. We're going to subtract 36 from each side, and we have X squared equals 64. Now we take the square root and get X equals 8. Is it plus or minus 8? No, because this is distance, and distance is always positive here in the real world. Now in bizarro world, it's maybe that's possible, but no. That's Pythagorean theorem. And again, only if you have a right triangle. Now, this is called a coordinate plane. This is the y-axis. This is the x-axis. Now, points are always in the form xy. I know always is a long time. But if we have, let's say the point 3, 5. This is the x. This is the y. This is very, very important. This is going to come into play in a whole lot of things that we do later on in the semester. Now, some people remember this as in the door, up the stairs. In the door means side to side. Now, this side over here is positive. This side over here is negative. Up is positive, down is negative. Okay, now both these numbers are positive, so it's going to be to the right and up. 1, 2, 3 in the door. Now up the stairs, or some people say run and then jump. Run means back and forth, and jump or up the stairs is this way. So 1, 2, 3, that's our on the x-axis. 1, 2, 3, and then up the stairs 5 times. 1, 2, 3, 4, 5. So that's the point 3, 5. And before I forget, we always start here. This is called the point of origin, and the coordinates for that are 0, 0. Now, what if we have the point -3, +5? -3, remember we always start here. -3 goes to the left. 1, 2, 3, and up 5. 1, 2, 3, 4, 5. -3, 5. And if we have -1, -5, again we start here. -1 is here, and then -5. 1, 2, 4, 5. -1, stupid -5. Okay, and again, this is about the most difficult, and it's not very hard. What if we have 5 comma 0. In the door, in other words, side to side, it's positive 5. So we go 1, 2, 3, 4, 5. And now where do we go? We do not go up or down. It stays right on the x-axis. So that's 5 comma 0. And what if we had 0 comma negative 3? Where do we go, left or right? Neither. We stay on the y-axis and we go down 3. 3 right here. And that is 0 comma negative 3. Okay? Okay. But the thing you want to really keep in mind here is that points are always in that form, x, y. Now the distance formula, you're going to see this, not a whole bunch, but you will see it. The distance formula. I sent you a sheet the other day with a lot of these formulas on it. This should be on there. Distance is indicated as lowercase d equals the square root of x2 minus x1 closed squared plus y2 minus y1 closed and squared. Looks real hard. It's really not at all. But if you'll look, what this is it's the Pythagorean theorem, just kind of moved around some. Like if we wanted to know the distance between 3, 5, and 5, 0, see? It makes a right triangle, and that's what this is. This is the Pythagorean theorem. Now, what we're going to have are 2 points, x1, y1, and x2, y2. Okay, so if you have these 2 points, 2 comma 5 and 7 comma 9. Okay, this is the first coordinate, so we're going to call it x1 and y1, but it doesn't make any difference. This can be the second coordinate, so we're just going to call it the first one, x1, y1. This is the second coordinate, so we're going to call it x2 and y2. Now we just plug in the numbers. x2 is 7 minus x1 is 2 closed and squared, plus y2 is here, 9, minus y1 is 5 closed and squared. Seven minus 2 is 5, so we have 5 squared plus, excuse me, 9 minus 5 is 4, 4 squared. So this equals the square root of 25 plus 16 is the square root of 41. As far as I'm concerned, you can leave it under the radical like that. That's okay with me. Okay, now, about as difficult as these get, excuse me, is if we have some godless negative numbers. Negative 6, comma 5, and 3, negative 4. Okay? x1, y1. x2, y2. So we have the square root of x2. Our formula is x2, which is 3. So we have 3 minus x1. Minus a minus 6 makes it a plus 6. Close squares. Everybody with me here? The formula says minus, or you can think of minus as the opposite of. the opposite of -6 is +6, plus y2 is -4, minus y1, which is 5, closed and squared. Now this is going to equal the square root of 36 is 9, 9 squared plus -9 squared. Now remember, when it's in parentheses like that, this will come out to be a positive number. So we have 81 plus 81, which is the square root of 162, I think. Now 162 is 2 times 81. Right. So this equals 9 times the square root of 2. Right. Okay, that's all we have. Y'all take care. Have a happy Groundhog Day. Bye-bye. Bye, Bonds.